In graph theory, we say that a graph G with vertex set V and edge set E is a bipartite graph if the vertex set V can be partitioned into two subsets, let's call them A and B, such that every edge in the edge set E has one endpoint in A and the other endpoint in B. Now, a bipartite graph has two interesting properties. The first is that a bipartite graph has no cycles of odd length. And the second property is that a bipartite graph is two-colorable, which means the vertices can be colored using two colors, for example, red and green, such that no two adjacent vertices have the same color. So let's check out a few different examples of graphs and determine if each one is bipartite or not. So if we consider this first graph right here, this graph has 6 vertices labeled from A through F. The easiest way to determine if this is a bipartite graph is by using this second property that we've listed right here. A bipartite graph is two-colorable. So that means that no two adjacent vertices can have the same color. So here's what we can do. First, pick any vertex that you want in the graph. So let's just pick vertex A to start with. Let's color it with some color. Let's call it green. The color doesn't matter, but we'll just choose green for this example. If this graph is a bipartite graph, it means that every vertex that this vertex touches needs to be colored using a different color. So we can see that vertex A is adjacent with vertex D and vertex E. In other words, it shares an edge with those two vertices. So if this is a bipartite graph, both D and E need to be colored using a different color than green. So we'll choose red for this example. So now let's consider vertex D. Every vertex that it touches needs to be a different color than red. So we can see it touches vertex A and vertex B. So A and B both need to be a different color than red. So A is green, that's good. So let's go ahead and color B green as well. Now if we move on to vertex B, since it is green, every vertex that it is adjacent to needs to be a different color. So it's adjacent to vertex D, which is already red, and it's adjacent to vertex F. So F also needs to be red. So let's color F red. And then lastly, every vertex that vertex F is adjacent to needs to be a different color than red. So we can see it is adjacent to vertex B, which is already green, and it's adjacent to vertex C. So C also needs to be green, so it can't be the same color as F. Now, what we'll notice is that we were able to color this graph in such a way that no two adjacent vertices have the same color. So what that means is that this is a bipartite graph. And what we'll notice is that if we consider our original vertex set, so that's just the names of all the vertices in this graph, there are 6 total vertices. So what this says is that we can partition this vertex set, or we can split up this original vertex set into 2 smaller subsets. Let's call it A and B. And the vertices that belong to each of these subsets are just the ones that align with the colors in the graph. So we can see here's one subset. So all of the vertices that we colored using green will be one subset, so vertices A, B, and C. So let's call that subset A. And then subset B is going to be this group of vertices, D, E, and F. So this is how we can partition this original vertex set into 2 smaller subsets. And we'll notice that for all of the edges in the original graph, each edge has one endpoint in this first subset, let's call it A, and one endpoint in this second subset, which we call B. So if we consider, for example, this edge right here, we can see that it has one endpoint in subset A and the other endpoint in subset D. And similarly, if we consider this next edge right here, it has one endpoint in subset A and another endpoint in subset B. And if we consider this next edge right here, we can see it also has one endpoint in subset A and one endpoint in subset B. So every edge we'll notice in this original graph has one endpoint in subset A and the other endpoint in subset B, which is the definition of a bipartite graph. So let's check out a couple more examples now. All right, now let's consider this graph right here. It has 3 vertices, A, B, and C, and we want to determine, is this a bipartite graph? So we can use the same process that we used in the previous example where we say, first, let's just pick some vertex. So let's start with vertex A. Let's color it using the color red. Now, every vertex that vertex A is adjacent to needs to be colored using a different color. So we can see that it is adjacent to both C and B. So both B and C need to be colored using green. But we'll notice when we do this that if we consider vertex B, every vertex that it is adjacent to also needs to be a different color. So it's adjacent to A, which is a different color, it's red, but it's also adjacent to C. And we can see that C must have the same color. So because vertex B and C are adjacent to each other and they have the same color, it means that this graph is not two colorable. As a consequence, it is not a bipartite graph. And one other way to verify that it is not a bipartite graph is by noting property 1 up here, which says a bipartite graph has no cycles of odd length. So a cycle is where we start at one vertex and then we move through the edges of the graph until we get back to that same vertex. If there is a cycle that has an odd length, then a graph by definition is not a bipartite graph. So we'll notice right away, if we start at vertex A and we move through the edges of the graph, so if we go to C, then B, then back to A, that cycle had a length of 3. In other words, there were 3 total edges that composed that cycle. So because it has a cycle length of 3, and 3 is an odd number, that's another way to quickly verify that this is not a bipartite graph. All right, now let's check out this graph right here. Is this a bipartite graph? So to determine if it is, let's again use the same trick where we just pick a vertex and color it any color. So let's pick vertex A and let's color it in red. If this is a bipartite graph, then every vertex that vertex A is adjacent to must be colored a different color. So for each of these vertices that A is adjacent to, they need to be colored green. So let's go ahead and do that. All right, now if we move on to vertex B, if this is a bipartite graph, then every vertex that vertex B is adjacent to needs to be a different color. So we can see it's adjacent to vertex A and vertex C. So both A and C need to be colored with red. So let's color C with red here. And then we can see that vertex C, every edge that it is adjacent to is already colored green, so that's good. Then if we move on to vertex D, every vertex that it is adjacent to needs to be colored red. So we can see it's adjacent to 3 vertices. So each of these need to be red. So A and C are already red. So let's color E red. And then for vertex E, every vertex that it is adjacent to needs to be colored green, which we can see it is. And then lastly, for vertex F right here, every vertex that it is adjacent to needs to be colored red, which it is. So we can see that this is a bipartite graph because no 2 adjacent vertices have the same color. And if we wanted to, we could note that the original vertex set looked like this. So this was the original vertex set, and we just saw that we're able to partition this vertex set into 2 subsets A and B, where A contains, let's say A is all of the red vertices, so A, C, and E. And let's say that subset B is all of the green vertices. When we partition the original vertex set into these 2 subsets, we'll notice that no 2 adjacent vertices have the same color. So by definition, this is a bipartite graph. All right, now let's consider this massive graph right here. We want to determine if this is a bipartite graph or not. When you have a graph that's really large like this, before you try the 2 colorable approach, it helps if you just first check, does the graph have any cycles of odd length? Because if you can find just 1 cycle of odd length, then you know right away that that is not a bipartite graph. So if we just look at these 3 vertices right here, at the end, we can see that we have a cycle of 3 right here, which is an odd number. So right away, because there isn't a cycle of odd length, this entire graph is not a bipartite graph. And again, the reason for that is if we did the 2 colorable approach, we would quickly find that if we colored this vertex green, then both of these vertices that it is adjacent to would need to be a different color. They would need to be red. But then we can see right away that these 2 adjacent vertices have the same color. So that automatically makes it not a bipartite graph. So just keep that trick in mind when you're trying to determine if a very large graph is a bipartite graph or not.